We have a spherical capacitor whenever we have a sphere surrounded by another sphere. Like here, we might have a shell or a full sphere surrounded by a shell of a sphere. Now, the sphere that's inside has a radius of R1, the other one, the inner radius is R2, and let's say we charge them with opposite and equal charges. For example, a positive charge here and a negative charge in the outer shell. Now, between the shells, the electrical field is going to be given by this expression. Okay, we can find that using Gauss's law, like taking a sphere, this dashed line here, as a Gaussian surface. The flux through that sphere is going to be just Q over epsilon 0, and Q would be the charge of the inner sphere. And from there, using the geometry of a sphere, since the electrical field is going to be constant all along the sphere, then we can find, like we did before, that E is given by that expression at any point on the sphere, and it's going to point radially outwards in every point of that sphere. Now, the potential difference, we calculate it like we usually do. It's going to be the work per unit charge to move one charge from this sphere here to this other sphere. And that's given by the dot product of the electrical field and the displacement. In this case, the displacement is going to be along the radius. So that's why we write the dot product as E dot dr. And we are integrating in this case from R1 to R2, E dr. So we replace the value of E. So K Q over R squared times the unit vector R dr. So when we integrate that, the K Q is going to come out of the integration. The R dot R, they are in the same direction, so that's going to be just dr. And we do the integration. The integration is going to be from A to B of dr over R squared. Remember, the antiderivative of 1 over R squared, or dr over R squared, is minus 1 over R. So here, this one is going to be minus 1 over R from R1 to R2. So the integration gives me 1 over R1 minus 1 over R2. That's the potential difference. So our expression is K, Q, 1 over R1 minus 1 over R2. The capacitance being equal to Q delta V, so we just do the calculations. So this one here, if we put it in the same denominator, that will give me KEQ times R2 minus R1 over R1, R2. So when we use that in this expression here, that gives us that. The Q's cancel out, and we end up with R1, R2 over K, R2 minus R1. That's the capacitance due to a spherical shell. Now, of course, remember KE is 1 over 4 pi epsilon 0. in this particular capacitor, of the look of it, to be able to hold it together, we cannot have empty space in between. We can probably have an insulating rod holding the one inside. We can do that to a certain degree if it is very thin. But normally, in a spherical capacitor, we are going to have a dielectric in between. The yellow stuff would be made up of a dielectric. In that case, instead of Ke with epsilon 0, it's going to be epsilon, where epsilon is the dielectric constant, kappa, times epsilon 0.